Hi, it's me, Mrs. Weir, and I'm back to discuss with you a little bit of chemistry. We're going to be going over Chapter 2 from your textbook. Not all of Chapter 2. I decided to divide this lecture into more than one video because it's such a long and such a dense chapter. I want to make it a little more manageable for us. So we're just going to be discussing the first 4 sections in this video. So let's go ahead and get started. I got a question for you. First of all, let me move myself over here. I got a question for you. What makes up living things? In other words, when you think about what you were made of, or maybe what the desk that you're sitting at is made of, or something living like the tree outside, or even bigger, what is the universe made of? We can answer this question in pretty much one word, and ultimately everything is made up of atoms. That's really what everything is made of. There we go. Everything is made up of atoms. And so the word atom kind of leads us into this idea like, oh no, are we going to be talking about chemistry? And the answer is yes. We're going to be talking a little bit of chemistry today. Why? Why are we talking about chemistry in a biology class? Well, the answer is because all life is made up of really molecules or compounds. And molecules and compounds, well, they're made up of atoms. And so we have to study chemistry in order to really better understand or even make sense of biology. Chemistry, it is the scientific study of matter and its changes, and we need to know some fundamental or very basic chemistry in order to understand biological processes, why things happen the way they do. Because keep in mind that within your body, you're a living thing, so in your body, chemical reactions are happening all of the time. And those chemical reactions are really what's keeping you alive. Living things really, if you boil them down to a very simple explanation as to what they are, living things, well, we're chemical systems or very tightly controlled chemical reactions that happen to occur in a very coordinated way so that we can experience life as we understand it. So, going back to this idea, well, what is the most fundamental thing that we can talk about? Well, matter, atoms, molecules, these all sound like words that you hear in a typical chemistry class. Well, every object in the universe, everything is composed of matter. And so if you remember back from maybe your elementary or even junior high science classes, matter is anything that basically takes up space and has a mass to it. And when we think about matter here on planet Earth, we're familiar with the idea of a solid, a liquid, and a gas. These are naturally occurring physical states on our planet. Interestingly, water is the only substance that can exist in all 3 states naturally on Earth. Not everything does that, but those are the 3 physical states that we do see here on this great planet we live on. So ask yourself, is your desk composed of matter? Absolutely, it's composed of matter. What about you? You're composed of matter. Neighbors sitting around you, are they composed of matter? Yes, we all are. We're all composed of matter. And interestingly, we're composed of, solid parts, liquid parts, and even gaseous parts. So how big or how small can we get when we're talking about, the levels of life? Where does atoms fit within our big discussion? Well, in Chapter 1, you might remember learning that living things are organized and they belong to a hierarchy. And so when we think about what is the smallest, most basic unit of life, what is the smallest thing that can exhibit all the units or all the characteristics of life, that would be a cell. Well, cells themselves are made up of smaller parts, organelles. And organelles, while they themselves are not a living thing, they certainly constitute a living thing. They constitute cells. Organelles themselves are made out of organic molecules, things like proteins, carbohydrates, lipids. Even those molecules themselves are made up of even smaller parts called atoms. So when we think about, what is it that we study in biology, atoms in a sense are the smallest thing that we can study. They're not necessarily alive, but they do constitute or contribute to this bigger living thing that we recognize, cells. And if we continue on through this levels, you might remember that cells make up tissues. Tissues, of course, make up organs. Organs make up organ systems. So you have like heart and lungs constituting your circulatory system, your respiratory system. And of course, if you have a collection of systems, you've got an organism, and then you can get into, ecological levels, organisms of the same type and of location. They can make up a population. 2 or more different populations make up a community, and 2 or more communities make up an ecosystem. And if you want to get really, really big, then we can talk about the biosphere. So since we're going to be talking about some basic chemistry today, we're going to be talking at a very, very small level. But this, if you want to get an idea of where in the conversation atoms fit in, well, they fit at the very bottom, in a sense, of the list, or at the smallest part of these levels of organization. So atoms, if I could define them, if I could explain to you what is an atom, well, the word atom in Latin actually means indivisible. It's literally the smallest thing that you can have that retains all of the properties of that type of matter. Atoms, they can chemically bond to one another. For example, let me move myself out of the way. Here we go. For example, if I look at a compound that has a formula of C3H8, this indicates that 3 carbon atoms and 8 hydrogen atoms have all chemically bound to each other. Here's a diagram of what that would look like. These little white circles here, they represent the hydrogen atoms, whereas the darker circles represent the carbon atoms. So I've got 3 carbon atoms here, 8 hydrogen atoms, and the lines between them in this ball and stick model, they represent the different chemical bonds. All together, when these atoms bind in such a way, they constitute regular propane gas. While propane gas is not a molecule that we see that is important to living systems, the idea is that we're just kind of explaining, how do atoms, how can they chemically bond to one another, how can they be arranged to form this thing like a compound. Well, where does the word elements fit in? Where does the word elements fit in? Well, an element and an atom, really, when you're using these 2 words, they're referring to the same thing. It's just different numbers, in a sense. If you have one individual atom, well, you've got an atom. But if you have a bunch of atoms of the same type, then you constitute an element. So an element, it is a substance that you can't break down into anything else. So for example, carbon, you can't break it down into anything else except carbon. Carbon cannot be broken down into hydrogen. It can't be broken down into nitrogen. Carbon is carbon. And so carbon as an element is made up of many carbon atoms, or many atoms of the same type. Other example of elements that you might recognize besides hydrogen and carbon, something like gold. Gold is also an element. And so when we say that atoms combine to form compounds, we can also substitute the word elements in there for atoms. Elements, they combine to form compounds, because again, you're talking about many, many different atoms of the same type. An example of a compound, good old table salt. Good old table salt. When you take sodium, which by the way is a metal, if you didn't know, and it chemically reacts with chlorine, this green poisonous gas, the 2 separate types of atoms, they combine to form something new, a compound known as, well, good old table salt, sodium chloride. So when we talk about elements, again, these are individual things that can't be broken down into anything else. But a compound is usually made up of 2 or more separate atoms, or 2 or more elements. A compound can be broken down. In other words, I can take sodium chloride, I can simplify it back to the things that were used to produce it. I can simplify it back to sodium and chlorine. Speaking of chemical reactions, you had one earlier when we were showing the formation of table salt. And when we look at chemical reactions, sometimes they're very elaborate looking to us, but if you know how to read them, they're not so confusing. When you look at a chemical reaction, you can show it, as we often do in this book, in pictures, like at the top, or sometimes we show it with chemical formulas, or sometimes we show it with just the words. In the case of the diagram that's here in front of you, we're showing all 3 ways. Let me move myself right there. We're showing all 3 ways, in pictures, chemical formulas, and words. So in a chemical reaction, you're basically separating one side with an arrow from the other side. Everything on the left side of the arrow, that is your starting material or your reactants. Everything on the left side of the arrow, those are your products. And so in a chemical reaction, these reactants are changed into products. That's what a chemical reaction is. All of the atoms that are on this side, they rearrange themselves and to form something new products that are different from what you started with. This particular reaction, this is known as aerobic respiration. It's the breakdown of glucose, a sugar, in the presence of oxygen gas to release water and carbon dioxide. These big sixes in the front, these are proportionality or coefficient numbers that tell us that we've got 1 part glucose reacting to 6 parts oxygen to give us 6 parts water and 6 parts carbon dioxide. Other chemical reactions that we worry about in chemistry, other chemical reactions, photosynthesis is a chemical reaction. Interestingly, aerobic respiration, here it is from the previous slide. Aerobic respiration is also chemical reaction, of course. If you notice, photosynthesis and aerobic respiration are the reverse of one another. So in the case of photosynthesis, the reactants are carbon dioxide, water, and sunlight, and the products are carbohydrates and oxygen. But when it comes to aerobic respiration, the reactants are carbohydrates and oxygen, and the products are carbon dioxide, water, and energy. So you can kind of see probably already in your mind's eye why plants and animals, they make such a good pair, one for the other. Plants, interestingly, can do both photosynthesis and aerobic respiration. Animals like us, we're limited to only aerobic respiration. This might give you an idea why we are so dependent on plant life, because they make for us, this is their product, the starting material that we need in order to sustain energy. Kind of cool, huh? Sometimes we use the word metabolism, a word that we learned back in chapter 1 to describe chemical reactions in living things. So when we say metabolism, we're talking about all the chemical reactions that happen inside an organism. Another word we use sometimes is metabolic pathway. So we can say photosynthesis is a series of chemical reactions. We can say photosynthesis is a type of metabolism, or we can say photosynthesis is a metabolic pathway. 3 different ways to describe the same idea that we're talking about. Isn't chemistry fun? Now I keep using the word compounds, sometimes I say molecules. What's the difference between these two? Is there a difference between these two? The answer is yes, there is a difference between a compound and a molecule. The answer to that difference is going to come from our periodic table. This is from your textbook, this periodic table, and real quickly, if something appears on this table, it's an element. Water, interestingly, is not an element because there's no water element, although the things that make up water are found on this table, but water itself is not an element. The periodic table is arranged in a very particular order, and basically you can think of it this way. If elements are in the same column, going up and down, or if they're in the same row, they're going to have something in common. When you take a basic chemistry class, you're going to study the periodic table and the trends between the elements in detail. We're going to deal with some of them in our biology class because they are important to us as living things. So here's kind of a zoomed in look at our table because I want to point out something to you. I've drawn in right here, here's element number 5, here's element number 13, and here is a stair-step line that I've drawn in that goes across diagonally, and it ends right here between element 51 and 52. So if you have your textbook handy, you might want to draw in this stair-step line because it's going to be an important landmark for us, and I'll show you why. Also, if you were looking on Blackboard, I made available to you a periodic table that looks like this. one that you can print. Notice again that that stair-step line is already drawn in for us on this periodic table. So I'm going to use this stair-step line here, like I said, as a reference point for the left and right side of our periodic table. Now, why are we worried about the left and the right side? Well, the left side of the table, so everything over here to the left side of this stair-step line, everything on the left side is considered to be a metal. There is an exception, and that's number 1, hydrogen. Hydrogen lives with the metals because sometimes it can react like a metal, but hydrogen, really, it's a non-metal. If an element lives on the right side, and I'm going to move myself here, if an element lives on the right side of the periodic table, over here, then that element is considered to be a non-metal. So yes, even though hydrogen lives over here, in a sense it should be over here with the non-metals, but it lives over here, like I mentioned, because it can react and it has some things in common with the metals in this first column. Well, what about the stair-step line? What if something touches that line? If something touches that line, it's considered to be a semi-metal, or sometimes we'll use the word metalloid. The one exception to that rule is the element aluminum, which is number 13. It does touch that stair-step line, but it is considered to be a metal. So now that we know the difference between the metals and the non-metals, that's going to make our discussion also a little more interesting. Oh gosh, I gotta find a better place to put myself. Okay, what's the difference, back again, between a compound and a molecule? Well, a compound can be a generic term. It means pretty much anything that's made up of 2 or more elements. But when we put the word ionic in front of the word compound, that's a little bit more specific. Really, the word ionic compound refers to anything or some substance that's made up of a metal and a non-metal. So something that lives on the left side of the chart as compared to the right side of the chart. A good example of an ionic compound is good old table salt. If you look at your periodic table, sodium is number 11. It lives in the first column all the way on the left side of the chart. Chlorine is number 17. It lives on the opposite side of the chart. Oh, wait a minute, I think I'm a liar. Is it number 17? I'm going to double check real quick. It is. So chlorine is number 17. It lives on the right-hand side of the chart. It lives in the second to the last column, or what we call group 17. Now the word molecule, really molecule is also kind of like ionic compound. It's a specific term. What it refers to is something that's made up of non-metals. So a good example is water. Remember that even though hydrogen lives on the left, it's an exception. It's the only element that lives on the left that's a non-metal. And oxygen, of course, lives on the right. It's number 8 on the opposite side of the chart. It's a non-metal. So here we have a compound made up of 2 non-metals, so that is by definition a molecule. So when I say compound, I'm talking about something that's made up of a metal and a non-metal. If I say molecule, I'm talking about something that's made up of 2 non-metals. I'll probably be using these a lot, and I'll try and again make sure to point out the difference between these two for the rest of the video. But the word compound, this is generic. It can apply to either an ionic compound or a molecule. Speaking of our periodic table, there's some things about our periodic table that we also want our students to know. And that is what you find inside any particular square or tile in the periodic table. So here's a nice example. Here is element number 6. All elements are listed in order of what's called their atomic number. And so the atomic number is going to be a whole number, like a 1, a 2, a 4, a 5, or a 6. The other number that's of any importance to us is a decimal number called the atomic weight. In the middle of the table, or in the middle of the tile, you usually have a large symbol that's 1 or 2 letters. In the case of carbon, its symbol is just a capital letter C. These symbols, these are the accepted abbreviations for any particular element. We're not allowed to make up our own abbreviations. We have to use the standard abbreviations that are provided for us on the periodic table. So again, I might say the periodic table of elements, or I might refer to atoms. It's just a reminder down here at the bottom that elements and atoms, they're somewhat interchangeable terms, where really when we talk about a bunch of atoms, we mean an element. But the periodic table, it is a periodic table of atoms or the periodic table of elements, however you want to think of it. When we look at an atom itself, an atom is actually comprised of even smaller parts. I know on a previous slide I said that atoms are the smallest thing that we study, and they are, but they themselves are made up of even smaller pieces. And so those smaller pieces of atoms are called subatomic particles. You might even recognize some of these terms. Atoms are made up of protons, they're made up of neutrons and electrons. When we look at an individual atom, where do we find these pieces? Well, an atom, believe it or not, is mostly empty space. But in the very middle of an atom, there's this core piece, which is what I'm kind of indicating right here, this core piece called the nucleus. Inside of the nucleus, you're going to find two things. You're going to find the protons, and you're going to find the neutrons. So what protons and neutrons have in common is that they're both located in the nucleus of an atom. Both of them are about the same size. So if you look at my slide here, both of them have a mass that's about 1 atomic mass unit, or 1 AMU. So they're both about the same size. The difference between protons and neutrons is their electrical charge. Protons have a positive charge, whereas neutrons do not have a charge at all. They're electrically neutral. And so what is the purpose of the existence of neutrons? It's probably to kind of stabilize the nucleus, because there's this huge collection of positive charge. And so since positive charges have a tendency to repel, the presence of the neutrons, they kind of act like a buffer, a binder, an insulator, so that those positive pieces don't just go flying apart. They're kind of stabilized together. In any particular atom, and we're using nitrogen as an example, the number of protons is going to determine what element you are. So if you look at your periodic table, nitrogen is number 7. No other element on the periodic table is going to have 7 protons. Only nitrogen will. If you have 6 protons, it's not nitrogen, it's carbon. If you have 8 protons, it's not nitrogen, it's oxygen. So however number of protons you have, that determines what element you are. Now when it comes to neutrons, the neutrons determine not so much what element you are, but what isotope, or what version of that element you are. We'll get into a little bit more isotopes in a couple of slides, but isotopes, or excuse me, neutrons, those are an important number too. When you look at an element, in the case of nitrogen, since it's number 7, it's going to have 7 protons. Nitrogen, if you look at its atomic mass and you round it to the nearest whole number, it weighs 14. That 14 comes from the mass of the protons plus the mass of the neutrons. So you can calculate how many neutrons any particular atom has by simply taking the atomic mass, in the case of nitrogen 14, and subtracting the number of protons. Where do electrons fit in all of this? Well, electrons, they're not located in the nucleus. They're located in an area around the nucleus, which we're going to refer to as a cloud. It's a region of high probability where you are most likely to find an electron. They can be hard to pinpoint. We know they're there, but it's hard to say exactly where a particular electron is at any time. Why? Because they don't stay still. They're moving around the nucleus at a very high speed. In fact, that's what we call electricity, is moving electrons. So we have these little particles that are moving at a tremendous rate around the nucleus in this space that we just refer to as the cloud. Electrons have an electrical charge. They are negatively charged. But in terms of their size or their mass, it is so small that we say that they have no mass. Now, even though these guys have no mass, they're incredibly important because they are what determine any particular atom or any particular element's chemical reactivity. So how reactive or unreactive, or how you will react, really it's determined by your electrons. Now you can determine how many electrons a particular atom has because an electrically neutral atom will always have the same number of protons as it does electrons. Nitrogen's kind of unique in that the number of protons, neutrons, and electrons is identical. That's not true for every atom. It just happens to be true for nitrogen. So, back to this kind of slide to kind of review it. Oh, let me move myself. Here we go. Again, atoms are listed in their order of atomic number. So that number 6 in the case of carbon, it's going to represent how many protons that particular element has. So for carbon, carbon's got 6 protons. The atomic weight at the bottom is going to equal everything that has a mass inside of the neutron. All of the mass of the neutron, remember, is in the nucleus. So this number represents the number of protons and the number of neutrons. It's the average atomic weight or the average atomic mass, but we just refer to it as the atomic weight, this decimal value. So which elements are important to living things? All of them? All the elements? Well, kinda. There's only 4 elements that we find make up the bulk of living things. That might sound surprising considering how complicated living things really are. But really, oxygen, carbon, hydrogen, and nitrogen, these are the 4 that we build all living things around. These are so important, so fundamental to living things, that they constitute almost 97%, 96.3% of all living things. The bulk of them comes from these 4 particular elements. Well, what about the other small smidgen, this piece of the pie? What elements are found in that part? All the rest on the periodic table? Not exactly. The remaining 3.7 or really 3.8%, most of that, 3.7, is made up of about 7 other elements. Which 7? Well, calcium and phosphorus, potassium, sulfur, sodium and chlorine, and a little bit of magnesium. The tiny fraction that's left after that are 14 other trace elements, what we need in just tiny minuscule amounts. It doesn't mean that these are unimportant. These are very important elements also. In fact, some of our vitamins cannot function properly unless we have the presence of some of these elements. When we think of minerals, when we hear the word minerals, minerals in our diet, really they're these 14 trace elements. And some of these 7 elements, these are the minerals that we need. And so even though they're present in only small quantities, don't think that they're not important. They're still very important to living things. It's just that most of our living things, or most of the elements that we use to make up living things, well, there's only 4 of them. That carbon, hydrogen, nitrogen, and oxygen. Those are the 4 biggies. So you might be thinking, this is weird. Earlier you mentioned isotopes. You slipped that in on us. So what are isotopes? Well, isotopes are atoms of a particular element, but they differ in the number of neutrons. So going back to this idea of, how do I identify a particular element, like in the case of nitrogen. Nitrogen is identified by, again, the number of protons that it has. So nitrogen's got 7 protons. But there are different versions of nitrogen. One version of nitrogen is called nitrogen 15. Nitrogen 15 doesn't have 7 neutrons, it's got 8 neutrons. And so nitrogen 15 is considered to be an isotope of nitrogen. When these numbers are all the same, like in the previous slides, 7 protons, in the previous slides, 7 neutrons, 7 plus 7 would have equaled 14. So nitrogen 14 was a particular isotope. 7 plus 8 is 15. So this is nitrogen 15, a different isotope. Remember that neutral atoms, and isotopes are neutral, neutral atoms have the same number of protons and electrons. We don't count these as a mass because they don't weigh anything. They're negligible. Other isotopes that you've probably heard of before are the carbon isotopes. Carbon 12, carbon 13, and carbon 14. Carbon 13 and carbon 14, you hear a lot about them because they're radioactive. That means that they're unstable and they decay over time. They literally change into something else. And when they do that, they emit radiation. Radioactive isotopes can be very important in medical applications. Barium, which some people have to swallow sometimes to light up the soft tissues on an X-ray. There's a barium isotope that it decays in about a few hours, but while it's decaying and emitting radiation, we can take a picture with an X-ray and capture that light radiation and use it to generate an image. Iodine also has various isotopes that we can use for medicinal purposes as well. But isotopes, basically the big difference between them is that they're going to have different numbers of neutrons. So in the case of carbon 12, it's going to have 6 neutrons. Carbon 13 is going to have 7 neutrons, and carbon 14 is going to have 8 neutrons. What they'll all have in common is that they'll all have 6 protons, because carbon, it's identified by having 6 protons. Similar, at least the word isotope, not so much the concept, but the word isotope and ion, don't get those confused. Ions are also important to living systems, and what these are atoms with an electrical charge. The way they obtain an electrical charge is that they're going to either gain or lose an electron. Remember that electrons have a negative charge, so if you gain an electron, you can gain negativeness. If you lose an electron, you lose negativeness. Whenever you have atoms that are gaining or losing those electrons, they'll become charged, and we change the name atom to the word ion. So looking back at our example of nitrogen, in this example we've got 7 protons and 10 electrons. We're going to ignore the neutron line for just a second. If we compare the protons versus the electrons, the question here is it positively charged or is it negatively charged? Remember that protons have a positive charge, electrons have a negative charge. So if we have an electrical imbalance here, we've got 3 more negative charges than what we do positive charges. So in this example, our nitrogen ion would actually be negatively charged. How many negatives? Well, it would be a -3 negative charge, 1 for each extra electron. Chemical bonds are based on the way that atoms basically play with their electrons. So there are 2 ways that we can form chemical bonds. We can do it by sharing electrons, or we can do it by transferring electrons and creating 2 oppositely charged atoms. And so when we think about chemical bonds, the 2 big examples are covalent bonds, number 1 on the chart up here. That is covalent bonds, and number 2, these are ionic bonds. Let's spend a little time talking about the big difference between ionic bonds and covalent bonds. Ionic bonds, oh my goodness, I think I duplicated this slide. I sure did. I duplicated this slide. Alright, well, we'll just go with it. So in a chemical reaction, when you have 2 elements, or when you have several elements that are kind of rearranging themselves, those reactants, what they're really doing is that they're playing with their electrons in the sense that they're taking their electrons and they're throwing them at each other, looking to see, what's going to form the most favorable conditions on the product side. And so sometimes they will gain electrons, sometimes they just release them, or sometimes they share electrons. Depending on what atoms in a chemical reaction decide to do with their electrons, that's going to determine what type of chemical bond they form. So we'll form ionic bonds when we have electrons that are transferred from one atom to another. Covalent bonds are going to be formed when atoms decide to share electrons between them. And we'll give you some specific examples. So looking back at our chemical reaction here, this is aerobic respiration. Here was glucose reacting with oxygen to form water and carbon dioxide. The electrons aren't shown in this picture, but the electrons from glucose and the electrons from oxygen, they're rearranging themselves in such a way to form these new compounds. The chemical reaction itself is going to decide how are these compounds going to be formed. Are they going to be formed by these guys transferring electrons, or are they going to be formed by these guys sharing electrons? And there's a way that you can tell. Ionic bonds, they're going to form when, again, electrons are transferred from one atom to another. Now, why does this happen? Well, in the case of sodium and chlorine, a sodium atom has a tendency to donate an electron, just one, to chlorine. When that happens, you have an electrical imbalance. Sodium normally has 11 protons and 11 electrons when it is a neutral atom. But when it donates over to chlorine, all of a sudden there's an electrical imbalance. In other words, sodium still has 11 protons, but now it only has 10 electrons. And so now we have an imbalance where we have one extra positive charge. And so we call that a positively charged ion, or we call it a cation. Whenever a donor atom donates a proton, that atom that did the donating becomes positively charged. And so we can refer to that positively charged ion as a cation. This is characteristic of metals. This is why metals are so good at conducting electricity, because they have a tendency to give away electrons. They have a tendency to form cations. What about the recipient atom? The recipient atom, because it's accepting an electrical charge, a negative electrical charge, it's going to have one extra. And so that extra negativeness is going to cause it to become a negatively charged ion. The word for negatively charged ions are anions. Non-metals are very good at accepting extra electrons. They have a tendency to form anions. So in the case of an ionic bond, it's formed because you have resulting oppositely charged ions. Those oppositely charged ions, they occur when the metal donates an electron to the non-metal. These are ionic compounds. In a covalent bond, atoms share electrons. There's no formation of ions. We don't even use the word ions when it comes to covalent bonds. In the case of a covalent bond, they can share one or two or even three pairs of electrons. Depending on how many pairs of electrons are shared, we refer that to as a double, a single, or a triple bond. So a single bond shares 2 electrons, a double bond shares 4, and a triple bond will share 6 electrons at one time. Oh, let me move myself out of the way. There we go. So in our diagram here, this is a typical water molecule. Water is formed with covalent bonds. Well, how does that work? Well, H2O, you have a central oxygen atom, and you have 2 hydrogen atoms that want to really, in a sense, be more stable. If you look here, they only have 1 apiece electron. That's what's being represented in this diagram. And oxygen on its outermost layer has got 6 electrons. Well, there's a rule of thumb in chemistry that says in order to be stable, you have to have, if you're a small atom like hydrogen, 2 electrons, or if you're a larger atom like oxygen, you need to have 8 outermost electrons. Well, 6 out here is 2 away from 8, and because hydrogen's a very small atom, it needs 2 to be satisfied, but it's only got 1. Well, a nice relationship forms here when this hydrogen decides to scoot over and get real close to this oxygen, and another hydrogen decides to scoot over and get real close to that same oxygen. Then all of a sudden, this hydrogen can share a pair of electrons between itself and the oxygen atom. Same thing for the other hydrogen. There's another pair of shared electrons. So there's 1 single bond here, 1 single bond there. Each hydrogen is satisfied. By the way, the oxygen is satisfied also, because now it's going to have that magic number that it needs 8 electrons in its outermost layer. So again, there's a rule of thumb in chemistry. The innermost layer, or small atoms like hydrogen, need 2 electrons to be satisfied, but larger atoms need 8 electrons. In this relationship, everybody's satisfied. These are covalent bonds because those electrons are shared. Covalent bonds form in molecular or molecules, in molecular compounds. So if you notice, water is made up of hydrogen and oxygen. Those are both nonmetals. Compounds that are molecules are all made up of covalent bonds. By the way, when it comes to who's a stronger bond, an ionic bond or a covalent bond, it turns out that covalent bonds are the strongest of all chemical bonds. We'll find out in later chapters. When it's time for us to make energy, we break down chemicals in order to release the energy stored in chemical bonds. It's covalent bonds that provide energy to living things, not ionic bonds. Now, to complicate matters a little bit, when it comes to covalent bonds, there are 2 types. There's what we call nonpolar and polar covalent bonds. Just as a reminder, covalent bonds, these are bonds that involve a sharing of electrons. Ionic bonds, there's no such thing as an unequal or an equal transfer of electrons. We're not worried about that here. But it's only when we're talking about covalent bonds that we're worried about how equally are those electrons shared between the atoms involved in the bond. If the atoms, they share all of those electrons equally, then we say it's a non-polar covalent bond. If one of the atoms kind of hogs or holds the electrons a little bit closer to itself, then the electrons are not shared equally between those atoms, and we end up with what's called a polar covalent bond. I'll show you the difference with some pictures here. So here is, let me move myself, there we go, out of the way. Here's a diagram showing the difference between polar and nonpolar covalent bonds. In the case of methane, CH4, we have in the middle of the compound a carbon atom. On the outside, we have 4 different hydrogen atoms. The reason this is a covalent compound, or a molecule, is because carbon's a nonmetal, hydrogen's a nonmetal. And so nonmetals share electrons. Now the reason that this is a equal sharing is if we look at the arrangement of this 1 carbon and the 4 hydrogens, nobody in a sense hogs the electrons that are shared. They belong equally to hydrogen as they do to carbon at each one of these positions. So because these are all shared equally, then in a sense the electrical charge is distributed equally all across the atom. So there is no net charge anywhere on this particular molecule. Compare that to a polar covalent bond. The word polar means that we have opposite ends. In the case of a water molecule, the electrons that are shared are not shared equally. We've got a central oxygen atom and 2 hydrogen atoms here on the ends. Hydrogen is a very, very small atom. Oxygen's huge compared to those individual hydrogens. The hydrogens don't position themselves directly across from one another. If you compare the hydrogens over here in methane, they're directly across from each other. These two hydrogens don't do that. They don't position themselves directly across. They're almost at an angle. Not exactly a 90-degree angle. It's about 108 degrees here between this atom and that particular atom. Well, oxygen is able to pull the electrons a little bit closer to itself than what hydrogen can. As a result, oxygen pulls more negativeness to itself. Here's another way to look at it. These arrows are indicating that the electrons are being pulled closer to the oxygen, so you've got a slight negative charge on the oxygen. Since you're pulling negativeness towards the oxygen, you're leaving behind slight positiveness. We say that water is a polar molecule because we have a negative pole and an opposite pole due to the unequal sharing of the electrons. Anything that dissolves in water is considered to be a polar compound. Anything that doesn't dissolve in water is considered to be a non-polar compound. You might have heard of the chemistry adage, like dissolves like. If you think of things like oil versus water, why don't they mix? Well, the chemistry answer is because oil is like methane. Oil is non-polar. Water, of course, is a polar compound. Non-polar and polar compounds don't mix. In living systems, there's lots of important non-polar or compounds that are more like fats, more like lipids. They have to dissolve to some extent in the water, which makes up most of living systems. And so living things, they play with the chemistry of non-polar versus polar in order to better absorb or to better get rid of certain materials. Oops, last slide, very last slide. This is kind of a closer look at this idea between polarity of water molecules or within water molecules. Here again is that diagram of water. The big red dot here represents the oxygen, and the two smaller dots here represent each hydrogen. So again, the positive charge is trying to emphasize that the hydrogens are positively charged and the oxygen is negatively charged. So that word polar or polar covalent bonds refer to that the electrons are not shared equally, and it gives the overall molecule kind of like a magnet, a north end and a south end. It gives that molecule a positive end and a negative end. We'll find out in our next lecture, our next video, that polar molecules have a tendency to form another type of chemical bond called hydrogen bonds. Water is a really unique molecule. Its polarity allows it to form these hydrogen bonds, and that creates a whole nother set of really interesting chemical principles. So that's the end of this video. I hope it's been helpful in explaining some of the basic chemistry that we like for biology students to learn.